Today, I learned a cool space fact. Well, maybe something a bit more personal. Picture this. You're floating 400 kilometers above Earth inside the International Space Station. You've just finished a meal. Maybe some rehydrated pasta, a tortilla wrap, and a sip of water. Then you feel the familiar pressure in your stomach. On Earth, you'd simply let out a burp and move on. But in space, it's not so simple. Astronauts can't burp the way we do. In fact, when they try, they risk something NASA calls a wet burp, where liquid and food come up along with the gas. This may sound like a minor inconvenience, or even a funny story, but it reveals something about our bodies. We are deeply adapted to Earth's gravity. After all, every person ever born was born here, and so we have to look at how microgravity changes digestion, NASA's experiments with fizzy drinks, and what this teaches us about human biology in space. Let's start with how burping normally works. Every time you eat or drink, you swallow small amounts of air. Carbonated drinks add more gas in the form of dissolved carbon dioxide. When gas accumulates in the stomach, it exerts pressure on the walls. At the top of your stomach sits the lower esophageal sphincter, a valve that normally prevents food and acid from splashing upwards. When pressure builds enough, the sphincter briefly opens and gas escapes upwards. You burp. Gravity helps here. Gas rises above the liquids and solids, separating itself so that what escapes is mostly air. That's why burping on Earth is clean, quick, and usually predictable. Now, imagine removing gravity. In microgravity, astronauts experience near weightlessness because the ISS is in constant freefall around Earth. Here, gases don't rise and liquids don't settle. Inside an astronaut's stomach, gas, liquid, and food all float together. There's no top for gases to rise to, no layering to keep things organized. So, when the sphincter opens to release pressure, it's not just gas that escapes. It's gas plus liquid, sometimes including partially digested food, hence the wet burp. NASA has recorded videos of astronauts playing with floating water droplets in the ISS. Tiny bubbles get trapped inside these droplets, unable to rise or separate. That's exactly what happens inside the stomach. On Earth, gas rises due to buoyancy, the difference in density between gas and liquid. Surface tension also plays a role, allowing bubbles to coalesce and float upwards. In microgravity, buoyancy disappears. Gas bubbles can't rise, and surface tension keeps them trapped inside the surrounding liquid. The result? Any gas in the stomach stays mixed with fluids, creating the potential for wet burps. Even carbon dioxide behaves differently. Normally, it escapes in small bubbles that rise to the top. In space, it gets trapped inside the liquid, causing bloating and discomfort. In the 1980s, Coca-Cola and Pepsi tested their products in orbit. Engineers designed special cans intended to prevent soda from spraying everywhere. Astronauts reported flat taste, bloating, and wet burps. One astronaut described it as drinking soda-flavored foam. NASA concluded carbonated drinks were impractical in microgravity. Today, astronauts drink flat beverages like coffee, tea, water, or powdered drinks. Digestion is already a challenge in space. Peristalsis, the squeezing motion of the esophagus and intestines, still moves food along, but without gravity, food doesn't settle in the stomach. And that's why astronauts' diets are carefully engineered. Low gas, low crumbs, easy to digest. For example, tortillas replace bread to avoid floating crumbs, and freeze-dried foods are rehydrated with measured water. Drinks are sealed in pouches to prevent floating droplets, and seasoning is in liquid form to avoid stray powders drifting into instruments. Astronauts have shared their experiences. Chris Hadfield, famous for playing guitar in space, said, "When you burp in space, you throw up in your mouth a little." Not exactly glamorous. Other astronauts mentioned that wet burps are rare because their diet minimizes triggers. But they are careful to always drink slowly and avoid carbonation. Burping isn't the only bodily function affected. Sneezing, coughing, swallowing all behave differently. Fluid redistribution in microgravity causes puffy faces, nasal congestion, and sometimes mild headaches. Even flatulence is affected. Gas doesn't separate as neatly in the intestines. NASA doesn't often discuss this publicly, but astronauts joke about it. These stories may seem funny, but they reflect the practical changes of daily life in orbit. Interestingly, studies on rats, mice, and other small animals in space show similar issues. Gas and fluids mix differently, and burping or regurgitating doesn't work the same way. This helps scientists understand basic physiology in microgravity and informs how we prepare humans for long-duration missions. So why does this matter? Because a simple burp reveals a lot about human adaptation. Without gravity, bones lose density, muscles weaken, fluid shifts occur, and even digestion changes. Burping is a small, funny example of a much larger challenge. Life in space requires careful planning, attention to diet, and constant adaptation to a world without gravity. So, the next time you sip a soda and burp, remember you're benefiting from Earth's gravity. For astronauts in orbit, it's not that simple. It's an experiment in physics, digestion, and human adaptation.